today we're going to talk about wind resistance. Now I think wind resistance is a pretty intuitive concept that a lot of us have a handle on. If you've ever stuck your hand outside of a moving car, you can feel that force of the wind pushing on your hand. That's actually the feeling of wind resistance. Another word that we have for wind resistance is drag. So you might see it by both names. So let's see if we can draw a little diagram and see what's going on here with wind resistance. So if I have a ball and it's falling, so that if it's falling, then it's going to have a downward velocity, v. And as it's falling, it needs to fall through air. So these dots here are representing air particles. And as it's falling through this air, it needs to push the air out of the way. So these air particles get pushed out of the way. And we can see what's going on here. And just one effect of Newton's law is that if the ball has to push the air particles out of the way, we can also think of the air particles pushing on the ball. So all those air particles together, they exert a force on this ball. And we call this the drag force. So we call that F sub d. So I'm going to write out the equation for F sub d, and then we're going to see if we can pull it apart and see what each individual part of it is. So Fd is equal to 1/2 times this character rho, which we'll talk about, stands for density, v squared, which is the velocity of the object, squared, times the coefficient of drag times area. Okay, so let's see if we can talk about what each one of these parts means. So first we're going to talk about velocity. I think that's kind of the most intuitive one here. If you've ever stuck your hand out of a car while it's moving slowly, you probably didn't feel very much force acting on your hand. But if you stick your hand out of the car while you're on the highway, you feel much more force. The reason why is because the velocity is part of this equation. So as we get more velocity, clearly we're going to get more force acting on our hand. Let's talk about the next one here is rho. So rho stands for density. So it looks like a P, but it's actually a rho, spelled R-H-O, and it's equal to the density of the air. So the density of air is actually 1.2 kilograms per meter cubed. So what that means is that if I was actually able to get a cubic meter of air, so if this is my cubic meter of air, this is a box of air where each side of it is 1 meter, that the mass of all the air particles inside this box, all those air particles, is going to be 1.2 kilograms. Okay, so clearly that has an effect on this equation as well. You can think about this in terms of water. If we look at the density of water, it's actually much higher than 1.2 kilograms per meter cubed. And if you think about trying to move your hand through water, it's going to be a lot harder. I mean, anyone that's ever swam or even stuck their hand in a thing of water would know that it's a lot harder to get your hand through the water than it is to get your hand through air above the water. So the density of the fluid has a lot to do with it. The next one we want to talk about is the area of the object that's falling through the air. So the area of the object is actually, let me get a color that will stand out here. We're actually interested in if I was standing down below this ball as it's falling towards me and looking up. What I'd see is I'd see the ball, and if I kind of draw this little area here, that's the area that I'm going to see looking up at the ball as it's coming towards me. And essentially that's the amount of area of air that this ball has to push out of the way. In a way, it's kind of a slice of the ball at its widest part. Okay, so that is the area here. And then the last one that we have to talk about is the coefficient of drag. So the coefficient of drag is a measure of how efficiently air passes over the surface. If we look at these three objects that we have here in this diagram, all of the parameters that we've talked about so far they would all be the same. We could think about this plate here. It actually has the same area, the same frontal area as this sphere. So this is a circular plate here, and this is a sphere. And this is a streamlined shape. So if we were looking at these as it was coming towards us, we would actually see the same thing. We'd see a circle here, we'd see a circle coming at us here, and we'd see this thing as a circle. It's actually a teardrop, but we'd see it. All of these would actually have circular cross-section as it was coming towards us. So everything that we've talked about so far would lead us to believe that they would have the same drag. But if we look at how the wind flows around them, as we look at the wind flowing over this thing, here the wind goes up, and as soon as it gets past it, it does all these little swirly things. And those swirls, it takes a lot more energy to spin that air around, and it creates this big kind of vacuum of space here, which actually makes it a lot harder to pass this plate through the air. If we look at the sphere here, the air comes up and it goes around. It's a little bit easier to get through, but then it still kind of swirls a little bit. It's a little bit smoother, still has another swirly part. If we look at how much it's swirling, though, this one is clearly much bigger than this one. So this one is easier to pass through the air. And then finally, if we look at the streamlined shape, where here we have this nice kind of smooth transition of air as it's going over, and only this very small little spot here where the air starts swirling around. This one is the most efficient at getting through. Okay, so the coefficient of drag kind of takes all this complicated stuff and it converts it into a very simple number. Okay, so here we have 3 coefficients of drag here, and the larger the coefficient of drag, the more force that it's going to take to push this thing through the air. So here with this plate, what we're looking at is a coefficient of drag of 2.0. I don't know if you guys can see that, but that one, the CD, is equal to 2.0. And coefficients of drag, just like coefficient of friction, they don't have units. So this is just 2.0, just a pure number. The coefficient of this sphere here is actually a coefficient of 1.2. And then finally, this streamlined shape is actually far more efficient at getting through the air. The coefficient of drag for that one is equal to 0.12. So it's actually 10 times easier to get this streamlined shape through the air than it is to get this sphere. And it's even more so than it is if it were a flat plate. So I have this example here that we're going to use to illustrate the force of drag that acts on these 2 cars. And I'm sure you can kind of predict just based on the names here which one is going to have more drag. But we're gonna go through the calculation and see how much more. So here we have a Hummer H2, and on the right here we have a Toyota Prius. So I have information that I actually gathered from Wikipedia, of all places, where they listed the coefficient of drag for the Hummer, as well as the frontal area for the Hummer. So this is, if we were looking at the Hummer coming towards us, what would be the area of air that this Hummer would have to sweep out as it's coming towards us. And then finally the same thing for the Prius, so we have the coefficient of drag and the area. So if we're just comparing the coefficients of drag here, the Hummer is clearly has a higher coefficient of drag than the Prius. And if we look at the shape of the Hummer, it actually makes a little bit more sense. The Hummer is very boxy. It's got a little bit more of the characteristics of the plate that we were just looking at. Whereas if we look at the Toyota Prius, it is a lot more smooth. It's got these smooth lines that go over it. So this one is a lot closer to the streamlined shape that we were looking at. So clearly the air is going to go over the Toyota Prius more efficiently. And then also the Hummer is much larger as it's coming towards us, so it has a larger area than the Prius. The Prius is a smaller car than the Hummer, obviously. So let's write out the equation for the drag force. We can think of the drag force. This is what I wrote before. Fd is equal to 1/2 times rho. Do rho in blue. Times v squared, which is the velocity of the car squared, times cd, which is the coefficient of drag, times a. Okay, so we're interested in the force of wind resistance that acts on each vehicle as it drives down the highway at 30 meters per second. So I'm going to get my color. So here our V is equal to 30 meters per second. Okay, so let's do the Hummer first, and then we'll figure out the Toyota Prius. So we're going to start with the Hummer. We do FD is equal to 1/2 times rho. In this case, it's 1.2 kilograms per meter cubed times V, which for this one is 30 meters per second, and that whole thing is squared, times CD, which for the Hummer is 0.57, and coefficients of drag do not have units, times area. And the area of the Hummer is 4.32 meters squared. Great. So I'm going to get out my trusty calculator here, and we're going to multiply this thing out. So I get 1/2, which is 0.5, times 1.2 times 30. And remember, I got to square my velocity, times 0.57 times 4.32. Let's see what that gives us. 1,329. Okay, so that's great. 1,329.6. We're just going to take the first 4. So that came out to be 1,329. So let's take a look at these units. Here I have meters squared in the numerator. Here I have another meters squared in the numerator. So that's meters to the 4th power. And I'm dividing it by meters cubed. So that'll take away 3 of those meters. What I'm left with is just 1 meter in the numerator. If I look at the other units that we have here, we have kilograms. There's no other kilograms in this equation, so I have kilograms. And what else do we have? The only other thing that we have here is seconds. So we have seconds, and that's actually squared in the denominator. So I have kilograms meters per second squared. And if we remember, another way that we can write kilograms meters per second squared, a simpler way to write that is the Newton. So this actually here, this whole thing here is the Newton. So we have 1,329 newtons, and that makes sense because newtons are a measure of force. So that's great, we're all set with the Hummer. Let's see if we can figure out the Toyota Prius now. So this one here is the Hummer. I'm going to do H2, and here we're going to do the Prius, P-R-I-U-S. So the force of drag is going to be equal to 1/2 times, again, we're going to have 1.2 kilograms per meter cubed. Then we have 30 meters per second squared, because they're both going at 30 meters per second. Now this is where it gets different. Here we're going to have a different coefficient of drag. The coefficient of drag here is 0.25, again unitless, and the area of this Prius is only 2.32 meters squared. So if we multiply all that out, let's see what we get. Let's take our calculator out. We are going to get 0.5 times 1.2 times 30 times 0.25 times 2.32. Oh, I forgot my square. 30 squared times 0.25 times 2.32. Always remember you have to square the velocity in this equation. You get 313.2. Okay, so let's write that in. 313.2. 313. 313, and again we have newtons here. Okay, so that should be pretty eye-opening here. Probably not a surprise, but the Hummer is clearly not nearly as efficient at moving air past it as the Prius is. Engineers spent a lot of time designing the Prius so it would be efficient at moving through the air.